Welcome to this special edition of the DECam Community Pipeline. Today, in this episode, I'm going to talk about the post-processing of the moving object detections produced by the pipeline when the data set being processed has 3 or more exposures in the same pointing in the broadband filters, and the appropriate parameters have been set by the operator. In this case, there's been a data set in GRIZ that took 3 fields with 5 or 6 exposures. They have finished processing and been put in the final dataset directory. We go to that final dataset directory with the shortcut CDQ. And the dataset is 724693, 220607. When the moving object detection system produces an output, it produces files which are to be reviewed and which tells you that this has happened. An alias to initially define commands to be used with the moving object detection system is MOV aliases, which takes a set of directories to be examined. So the command MOV is a quick check to see are there any files. In this case, there are 17 sub-data sets that were looked at by the moving object detection system. Not all such data sets will produce detections. So similarly to MOV, there's GRP check, which finds the files that say at least one candidate object was found. In this case, there are 7. We can do another quick check to see what was found with GRP all. And the important thing to look at here is, well, this is the data set. You see different pointings, mostly the same pointing, the different filters, and this is the processing ID. These are the unique names that the detection system assigns. This is a group identifier, and this is the number of detections within a particular pointing, and it has to be 3 or more. So when you see 4, 5, and 6, that's going to be a very solid detection. These groupings are called tracklets. Then this is the rate, and over here is a score of how unusual or important this might be. What we see here is that at low rates, there are a number of solid detections which will be reviewed. And then at very high rate, these are almost always going to be some kind of junk, cosmic rays, edges of bright stars, and so forth. But we want to review all of them to see to get rid of those which are not real before we report them, and to confirm those that are real. There are many different types of situations, some with very few detections and some with a very, very large number, where reviewing the results can be very difficult, and there are other techniques that one can use to simplify that. For this, it's very few. They're relatively bright. This is the magnitude in whatever band. So this is not going to be a particularly unusual situation. The detections are grouped into 3 categories. A, for apparent rates less than 10, which may be distant objects and are generally unusual. B, which are apparent rates greater than 100, and C, which are rates between 10 and 100. This subgrouping makes it easy to separate things during the review. To do a review, I check for things that have not already been reviewed and or submitted to the database and the Minor Planet Center. So we'll check if there's any in the A category. There are none. We know there's some in the B category. There are 3. A list dorev.list is created. That is, drives the next step. So now we start up an IRAF session and load the MOV package, which has all the tools that are used in this process. We would also start up an image display. There is one already started up. And the command that's used to do this review process is do rev. So this is telling you we're starting with the first of 3, which data set, what the situation was for the group. So there was 5 exposures, 60 seconds long, separated with over an hour. And then the first tracklet with its rate, a percentage error of the rate, which can be useful to decide that something is not real. And over here, it tells you that there was 3. So we look at the image display. Clearly, there was nothing there. It was just detecting positive deviations here in the wings of this star, and here in just a noisy exposure, maybe clouds were present. So we are able to type various different keystrokes in this review process. I will use Z, which says find all other places where that it was found, and those particular 3 were found, and mark them as not useful, and then delete them. In this case, there was only 1 in this particular set. And so ultimately with the Z and then D, which means delete. And then after deleting it, there were no longer any images or data or groups, another word for tracklets, to be found. And it goes on to the next one. In this case, there are 130-second exposures. It found 6 candidates. This is a common occurrence. Very, very bright stars will leave some residual of the bleed trail, even though the pipeline tries to mask it out. Because they will all be in the same CCD and roughly at the same Y, meaning up and down, which is DAC, special key Y, can quickly remove everything that is in that CCD within a few arc seconds of this declination. Otherwise, you'd have to delete one by one. So I'm typing Y. It says it deleted 5 nearby positions in the first image. And these were all CCD 59, and ultimately they all get deleted to no data. And in fact, in that case, every of the 6 candidates, they were all caused by the same problem. And here we go to the third one. And this is going to be very similar. You see the line. So I'll use Y again. And it deletes all those, and we're done. In the process, it will have deleted the files that aren't useful, which we're not going to want to save. So we've done A and B. Now let's look at the C class, where the real common variety asteroids are found. So there are 4 pointings that have this, that found tracklets. I do the do-rev again. This pointing is in a very challenging, crowded field. And this shows the power of the moving object detection system. Very few of the surveys looking for asteroids would even try and look here. I look at this, the way one would normally look is to see if it's consistent. Normally they'd be found in the center unless it's near the edge. This interpolation of the edge is the giveaway that it's near the edge. So it's really hard to visually see that, but I know from experience that this is going to be a real detection. So the default setup, I use spacebar to accept it. That's the spacebar is transformed to plus, which means accept. Now it goes on to the second one, which also had only 3 detections. Again, one could study this closely, but I believe this is to be real. That's one reason why these are all going to be bright, is that faint things in such a crowded region would not be likely to be found. Spacebar. Now the default setup in do-rev right now is if there are 4 or more measurements in a tracklet, then it's automatically accepted. So this one with 6 is automatically accepted. It had a brightness of 16.3, very bright, very common asteroid. Here's another case of 3 that we accept, and the rest were automatically accepted till we get here to tracklet 15 of 21. Yes. Slightly fainter, but it's clear it was found within the gaps between the stars. And now it went through all 21 tracklets. It came around to the first one. And we're ready to quit and accept everything, because we didn't reject anything. If we did Q, it would rewrite the file, taking out everything that was deleted, but that would be an unnecessary step, which can be slow. So the quick mode is capital W. Now we're on to the second field. It found only one tracklet. The tracklet had 4, was automatically accepted. In this case, it says it knows that when it wrapped around, it was an automatic acceptance. So all it does is ask, we want to redo the data products, the files that are used then to build the final database. We don't want to redo it again because the cutout file is perfectly fine. So we say N for no. And now go on to the third of 4, found 7 tracklets. First one was automatic, the second one has 3. It looks correct. Next one was 5, automatically accepted, then another 3. Accept. Another 3, 507. It's fainter, but it looks clearly correct. Then it finishes, asks, do we want to redo the data products? Answer no. And then the last. And these have been the same field, but in different filters here. This one's Z. Okay. And it wrapped around, so we'll do the capital W. If instead I said, let's accept it again, then the next one was an automatic. And so I've gone through everything. And we're done with the reviewing. I will iconicize this, the display. So for now, we've reviewed everything. Don't need this IRAF session. At this point, the cutout files have all been reviewed. The data products, which means files that are little text catalogs that have the information that will be turned into SQL, which will be turned into entries in a database. Oops, I shouldn't have gotten out of the MOV package quite yet. After the review, we want to ingest into the Asteroid database. So a lot of commands for this are ADB ingest. The default is set for the most common thing, which will go through all of those files and build the SQL files and ingest them. All of these errors are because at multiple times it's trying to submit the same information about the images, the higher level information, not the individual tracklets and their measurements. So it built the SQL files and put them in the ADB database. The ADB database contains millions of measurements and detections and tracklets. Right now, we want to look at just the ones that have been reviewed, but have not been submitted to the Minor Planet Center. First step is to add some additional information, which is the release date from the archive metadata. And now the most common tool for examining things, ADB select. By itself, it will list all the objects that have been ingested, have not been submitted. And in this case, the PI histogram from the deep drilling transient program, the prop ID, the filters. Because these fields were outside of the Pan-STARRS footprint, which is used for calibrating the photometry for fields that are sufficiently far north. These have been calibrated against Gaia G. The night of the observation, which last night. The release, in this case, this was made public immediately. And then the number of distinct tracklets, in this case. ADB list will now show us everything. Now, because these are multiple use of different filters, they may be the same asteroid. So we can try and join them together with the command ADB interleaved -F, which says do it across filters. Otherwise, it will only try and join things within one filter. And we'll allow a magnitude difference of 1 because they're different filters. And now it says there was one case that was 2, and there was one case that had 3 detections across 3 different situations. Now, if I do an ADB list, we'll see some of them have been joined. These 2, NG and R, they have essentially the same position angle, similar magnitudes, and of course their orbits or their tracklets join on the sky within a certain number of arc seconds. Occasionally, if it was not sure whether something might have been done wrong, I could plot up ADB plot that particular tracklet or set of tracklets. And yes, they form something that looks like a track. It looks like there's a couple offset ones, but it's still fine. Q to quit. Another occasional problem that occurs with the moving object detection system is when it can detect the same object with different combinations of images. And so ADB MPC will check for that. If this is not checked and there are that, then there'll be duplicate positions for 2 different possible sources, and the Minor Planet Center will reject the submission. Just to demonstrate some various things that are done, I can again select. There are many options. So if I want to select with digest scores 65 to 100, which is what is reported as possible near-Earth objects, there are none. I'm going to select all of them. Basically, what ADB select does is it makes a subtable that other tools in the ADB class use. Since ADB MPC check will list the records for one measurement in each of the what it considers to be distinct asteroids. This can be plugged into the MPC Minor Planet Checker program, and if I were to do this, I would expect all of these to have been previously known asteroids. We might as well do this just to see. So I cut out all these records. Go to the Minor Planet Checker, search around these observations, paste in the observations. DECam has much higher accuracy than this was initially designed for. I like to look at the total rate rather than the separate rates. And now we ask it to tell us what it knows about these positions. This list produced by ADB MPC check is ordered by reverse order of magnitude, because mostly the first ones are the ones that are more likely, the fainter ones are likely to be unknown and therefore new detections. So the first one at 20th magnitude was this numbered asteroid. And we scroll down. And as predicted, everything is a known asteroid. In fact, they're all numbered asteroids. And this is a consequence of short exposures, the crowded field. But we report these anyway. So the final step is to report them to the Minor Planet Center. ADB MPC send has various options, but I'm just going to send them without any review or any further ado. Sent the R observations, now it's sending the Z observation, and finally G and I. I have it set up to keep a record. So these are the files that were sent and a record kept in email. So we got 4 acknowledgements of the submissions. That's good. And I'm going to save them. in my email folders. And I'm done post-processing these observations from that particular program. So, good day.